All right, so here's the part of the show where you have to actually take these equations for a spin. So let's call this one projectile practice problem number one. Well, that's tough to say, projectile practice problem number one. And it says, a plane flies at 267 meters per second horizontally and drops a bomb which takes 35 seconds to fall to the ground. So there's three parts to this one, and part one says, number one, how far does the bomb travel horizontally before it hits the ground or hitting the ground? Number two, how far does the bomb fall vertically? And three, with what vertical velocity does the bomb hit the ground? You're going to do give and want. You're going to set this one up and just try your best on this one. And some people, you might actually surprise yourself because you're like, oh, this doesn't actually seem like too difficult a problem. But do the give and want. Take it as far as you can get. And when you feel like you've taken it as far as you can go ahead and hit play and you'll see the solution pop up. All right, so hopefully you got a chance to take a look at this one. Let's take a look at the solution. So a couple things. This is an awful drawing, and I apologize. I did my best, not the best artiste. But we have our plane here, and they say it's flying at 267 meters per second horizontally. So over here, I just drew, you have a plane going to the right, basically, and they're going to drop something from their plane. And if the plane was not moving horizontally, that object would have just dropped straight down, kind of like our free fall problems. But what's going to happen is, since it's moving horizontally, the object's going to travel forward right underneath the plane here. So for givens, VOX is 267 meters per second because that's the speed of the plane horizontally. And the plane is not moving at all in the y direction. It's going all in the x. So your initial velocity in the y direction is actually 0. They tell you it's 35 seconds before the object hits the ground. And then we always have our buddy gravity is negative 9.81 meters per second squared since it's an acceleration. And we're looking for three things. We're looking for delta x, delta y, and vy. So the only equation we have for delta x is the one we just wrote down. So we have delta x is equal to VOX times time. And we look up, we have VOX, we have time, so we just got to multiply them. And that means that this object moved a distance, horizontal distance or displacement of 9,345 meters. All right, part two says how far vertically did it fall, which means it's looking for delta y. So you go equation shopping, which is the best type of shopping, and you say, okay, well, I'm going to use delta y equals VOIT plus 1/2 GT squared. And what's nice about this, the plane's moving all horizontally, so the VOI is 0, so this term just goes away. And then you just have to do delta y equals 1/2 GT squared, and it means that bomb in this case fell down. It's negative 6,008.63 meters. All right, then last but not least, they say how fast was the bomb going vertically when it hit the ground. So you go equation shopping again, and you need to find one where it's Vy. And the only one you have that has a Vy equals something like this, that has a time, is Vy equals VOI plus GT. So you can see we just kind of plug and chug. And then you'll look and you see negative velocity, and that's because the object's falling down. And in physics, we usually define things that fall down as being negative. Cool, so that's not too bad a one. It is tough if you don't remember what the symbols are. So if you're having trouble with the symbols, just go back to our warm-up and take a look and see if you get the symbols down again. All right, practice problem number 2. This is based on a true story too. It says, while flying to a physics teacher conference in Hawaii, Mr. T. Laurent and Mr. K. Laurent ensue in a struggle for an autographed Taylor Swift CD they find randomly on the floor of the plane. It suddenly falls from the plane. The plane from which the CD was dropped was flying at an altitude of 500 meters, and the CD travels at a horizontal velocity of 233 meters per second. And the question here is, how far does the CD travel horizontally? So take a moment. For sure on these problems, you have to do give and want equation numbers. So try to get all the givens. And then the want is right here in yellow. It says, how far does the CD travel horizontally? And so they're saying horizontal distance, basically, in this case, is going to be your change in x, or your displacement there. So take a moment, hit pause, see how far you can take this one, and then when you're ready, go ahead, hit play, and then we'll go through the solution. All right, so this one's actually a little tougher, but I will say my plane looks better. So I had a little practice. So again, similar, we have a plane flying to the right over here, and they tell you that VOX is 233 meters per second. And then my brother and I are struggling for Taylor Swift CD, good CD. We drop it, and then we know a couple things here that are different than the previous problem we did. They tell us in this problem, we know that the CD is going to fall 500 meters. So since the CD is falling down, notice we made it negative because displacement here, the vertical displacement's a vector, and I've kind of been lazy and not put my vector symbols over the y, but technically I should have put an arrow over that. But it's going down 500 meters. We know that the plane's flying horizontally again at 233 meters per second. And since the plane's going all horizontal, that means your VOY is again 0. And then we always have our buddy gravity. Since we're on Earth, we will do some problems where we go to different planets, but just assume we're always on Earth unless they say we're on some random planet. But in this case, if we look back, they want your horizontal distance that the CD travels from when it was initially dropped. So they want your delta x. So you go equation shopping again, which again is the best kind of shopping. And the only equation that we have for delta x is delta x equals VOX times t. So we look up and we're like, okay, we have VOX, it's 233, but we don't have time. So in this problem, it's the first type of problem where we're going to have to get the time and then come back and use this equation. So I just made a little note here. It says we need time. So we're going to have to use the other givens, the delta y, the VOY, and the g, to use an equation to solve for time. How much time does it take to hit the ground? And when you look for an equation in this case, you're like, okay, well, I need an equation with a delta y. So I have delta y equals VOYT plus 1/2 GT squared. And in this case, again, since VOY is 0, that term just goes away. And you're going to get delta y equals 1/2 GT squared. Bam, right there. And then we need to solve this bad boy for time. So I kind of showed the steps a little bit, but basically it's 1/2 g. So you're going to multiply by 2 on both sides and divide by g on both sides and then take the square root. And when you do that, this is actually a pretty handy equation to have. It's going to be equal to, time's going to be equal to the square root of 2 delta y over g. And then now you plug and chug because we have delta y is negative 500 and you have g is negative 9.81 meters per second squared. And the negatives will cancel. And you do have to be careful there because sometimes people will forget to throw the negative onto the 500. But it is negative 500 because the CD is traveling down. And you can imagine back to math class, no pun intended there, but if you have a negative under a square root, because maybe you just had the negative from gravity, acceleration there, your calculator is going to give you imaginary numbers. So just think physics is very, very real. We should get real numbers. So you got to have negatives on top and bottom of that fraction. And then it's going to turn out to be around 10.1 or 10.096 seconds. So we use the y direction information to get our time. And once we have that, then we're like, okay, well now I'm just going to take our time and we're going to plug it back into this equation where we needed time right there. So we're just going to do VOX times time, which means this thing traveled at horizontal distance of 2,352.46 meters. All right, we'll do one more practice problem and then we'll call it a day here, I think. So that was number 2. Let's try a numero trace. Let's go projectile practice problem number 3. So it says Billy Joe is bored, so he stands on a bridge kicking stones into the water below. And then I made a note, this is before smartphones, because I think that's basically what I did before a smartphone. If you're just out in nature, you just kind of kick stones into the water and kind of took walks and things before people stared at their phones all the time. But it says if Billy Joe kicks a stone horizontally with a velocity of 7 meters per second, and it lands in the water a horizontal distance of 5.4 meters from where he was standing, what is the height of the bridge? And go ahead again, we're going to do given want equation. Try to draw a picture. This would be probably pretty helpful. And then label your givens on the picture. And then we'll come back when you're ready to go through the solution. So go ahead and hit pause and try it out. All right, we're back. And I'll just say one thing that's kind of cool about this. So these are all kind of very practical examples. Like if you have certain measurements, you can figure out like how tall bridges are. You can figure out how far things will travel horizontally if they're launched at certain speeds. So you can kind of see where this maybe is kind of the foundation of rocket science, right? How you launch things into outer space and things like that. So here's our solution. And there's Billy Joe right here. He's happy. He's kicking a rock into a river. So it says you're kicking it horizontally. VOX equals 7 meters per second. And that phrase horizontally is basically telling you whenever they say you kick something horizontally, that's their fancy way to say VOI is equal to what? 0. So for my givens over here, notice I have both of those listed. again, we have our buddy gravity, negative 9.81 meters per second squared. And they tell us in this case, it's going to travel, the stone's going to travel 5.4 meters before it hits the river. So we're looking for delta y. So we go equation shopping again, and we say delta y equals VOYT plus 1/2 GT squared. And then in this case, VOY is equal to 0 because it's going horizontally. So we'll say that's 0. So our equation simplifies to delta y equals 1/2 GT squared. So I'm like, okay, let's look at our givens. Do we have gravity? Yep, we got gravity. Do we have the time it takes? And again, we don't have time. So I think to myself, okay, time is the link between our y equations and the x equations. So I'm going to say I need time. So I'm going to go look at my x equation, and I say, okay, delta x over here equals VOX times time. And I look back up and I'm like, oh, that's cool because we have delta x is 5.4 meters and we have VOX is 7. So we can actually use our information in the x direction to get time. So you can see here I solve the time equation is just equal to your delta x over VOX. And you plug and chug and you get, it took about 0.771 seconds for that stone to hit the water. So once you have the time, then you're like, okay, I got my time. Now I'm just going to go back and I'm going to take that time and plug it in for the time in this equation. And when you do that, you use delta y equals 1/2 GT squared. You're going to figure out that basically that stone fell down, since it's negative, 2.919 meters. So you could say the height of the bridge must have been positive 2.919 meters. So that's a lot of information, but those are 3 really good projectile examples. So if you can do those 3, you're in pretty good shape. One physics all-star question before we go. If you don't feel like being a physics all-star, just go ahead and stop the video. But if you want to be a physics all-star, try this one out. It says, skydiving and baseball, and I probably say don't try this at home. It says you decide to jump out of a plane with your buddy, and while falling, decide to play catch with a baseball. And we'll say there's no air resistance because it makes the problem easier. But imagine you're falling, you're looking across to your buddy, you're both falling. Obviously, you're wearing parachutes, so this is safe. How should you aim so that your throw hits your buddy right in their hands? So if you picture it, again, I'm not the best artist, but basically you have one person over here and they have the ball. So there's the ball. And then you have your buddy over here. And skydiving wasn't exciting enough. So you're like, well, let's do a physics experiment and we'll tell Mr. Laurent the results. But imagine that there's no air resistance and you want to throw this ball to your buddy. How should you aim? And we'll assume that wherever you aim is actually where you're going to throw, because sometimes that's not the case. But how should you throw and aim, or aim and throw, such that you hit your buddy right? So think about that for a second. I guess the options would be you could aim up, you could aim at them, or you could aim down. All right. So the answer to the physics all-star question, gravity, the acceleration from gravity is going to accelerate everything at the same rate. And we're assuming there's no air resistance. So that means friend number 1 and friend number 2 would be falling at the same rate. And the baseball, since we're ignoring air resistance, would also be falling at the same rate. So this is kind of a trick, but you'd actually aim right for your buddy's hands. So the reason why that is because as soon as you let that go, gravity, the acceleration from gravity will bring the ball down as well. So even though you aim straight, it'll still be falling vertically down. So sometimes I'll have students say, well, Mr. Hunt, shouldn't you aim down? Because you know your friend's going to be falling down. And I'd be like, yeah, but you're not taking into account the ball. As soon as you throw it, will also be falling at the same rate. So you can actually just aim right for your buddy's hands and know as soon as you throw it, everything's falling at the same rate. So kind of a cool question. Maybe don't try it out because it seems dangerous, but it's kind of a good theoretical question. We'll stop there. That was a lot of information. Have a wonderful day and go physics.